All right. Hello, welcome. This is going to be the first of my series in linear algebra, and we're just going to start talking about some vector stuff, some vector arithmetic that you may have seen in like a pre-calculus class or something, but you may not have, and if you haven't, it's not a big deal. I'm just going to show you right now. Okay. First, I need to define kind of the space that we're going to be living in for the most part in this class. Okay, and that's going to be Rn, the set of all n-dimensional vectors. Okay, it's a set of all possible n tuples of real numbers. Okay, so for example, R3 is the set of all possible three-dimensional vectors, which we oftentimes are going to refer to as space. R2 is the xy plane, right? It's the set of all possible xy pairs. R was the set of all sets of one real number. Well, yeah, it's the number line, okay? I'll just, for example, the vector v equals 1, 2, 3, 4 is an element of R4 because it has 4 components here. Okay? The next thing I'm going to define for you is the length of a vector. Okay? Magnitude of a vector, absolute value of a vector, whatever you want to call it. So if v is a vector that's an element of Rn, then the length of v is equal to the square root of the sum of the squares of the components of v, like the Pythagorean theorem. Okay, and I think, it's one of those things where for 3 dimensions, I'll show you in class. I don't want to waste your time on the video drawing the rectangular prism and marking off the diagonal and then the other diagonal and showing it's the same. You just do the Pythagorean theorem in higher dimensions. Okay, so it's going to be the square root of the sum from the first component up to the nth component, right? Because it's an element of Rn, there's going to be n components of, the ith component of v, so that's vi squared. Okay, that's the definition of the length. So, for example, if u equals 5 and 12, and that's a vector in R2, the length of u is going to be 13. Okay, length of u equals the square root of 25 plus 144, which if you know your triples, that's going to be 13. Okay, that's how we take the length of a vector. That's something we're going to be doing regularly in this course. Okay, I think the next thing I need to tell you about is the dot product. Okay, so I might actually shift over so you can see the entirety of that side. Oh, okay, that's good. So for the dot product, we're going to learn about 2 different ways, the dot and the cross product, that we can take 2 vectors and multiply them. Now, we're going to get different types of things back, right? For the dot product, we're going to multiply 2 vectors together, and it's going to give us a number back. And we'll see, this property about it that kind of gives you a hint as to what this is really about. But I'm going to define if, say, A and B are elements of the same Rn, right? They have the same number of components, is really what that means. Then the expression A dot B is equal to, what we're going to do is we're going to take the corresponding entries of A and B, we're going to multiply them together, and then we add that to get a total. And at this point, it's like, well, why would you do that? But I think over time, you'll see why a person would want to do that. So it's the sum of, and you know what, actually, I'm going to come back and fill this in after I've done an example for you. So for example, I'm going to say if u equals 2, negative 1, 5, and w equals 0, 1, 3, then u dotted with w, like I said, we're going to take the corresponding entries, multiply them. So it's going to be 2 times 0, okay, plus -1 times 1, plus 5 times 3. Okay, that's going to be 0 minus 1 plus 15 is going to be 14. Okay, and that's how we dot two vectors. So what did we do? We multiplied the corresponding entries. So what it's going to be is, okay, I'm going to need to index this as I runs from 1 to n. Okay, and what's going to happen? Hold on, I lost myself. Oh, I'm multiplying corresponding entries. So that's the ith entry in A multiplied by the ith entry of B. Okay, we multiply and then add. That's what we're saying now. Okay, that is the definition of the dot product. Okay, I'm going to pull that example away. Looks like I'm going to go get an eraser real quick. All right, so yeah, I'm going to give you a theorem right now. Now in this class, I'm going to generally prove the theorems for you in class. This one, in order to keep the video short, I'm going to actually record the proof of this as a separate video. And yeah, also because it's lunch, and I think I've got a class coming in for too long. And so I'm going to try to keep this video short. I will prove this, but it'll be a separate video. Okay, and this is like the cosine property for dot products. So the quantity A dotted with B, that's a real number. That's equal to the length of A times the length of B times cosine of theta, where theta is the angle between A and B. Okay, so this is really nice. This allows us to, you know, if we have the two vectors, we can compute the angle between them. There's obviously other things we could compute from this formula. Okay, no proof going to be given right here, but a big corollary to this is going to be really relevant to us really for the rest of linear algebra and multivariable calculus and differential equations, is going to be, and you know, I'll probably prove this one as well in that same video, that A and B are what we would call orthogonal in this class, which you would have considered perpendicular in the past. A and B are orthogonal if and only if A dotted with B is equal to 0. And so I'll let you see why that might be true in terms of this. If and only if A dotted with B is equal to 0. Okay, that's going to be something that I'm going to use throughout the course. Okay, I think now I'm going to shift back over here, and I'm going to talk about cross product. And I'm going to kind of go in a different order from usual right now. I'm going to actually cross two vectors for you, show you the algorithm, then I'll give you the definition, then I'll talk to you about what it means, okay? Which is probably not, you know, what you're supposed to do, but I think the most important thing for me, like right now, first week of school, is that you get some practice in crossing two vectors and that you know how to do it. And then over time, I'll show you all these different things that we're going to use it for. Your physics class, you're going to learn about reasons you will cross two vectors. So I'm going to define the cross product, or I'm going to set up for that. If A and B are elements of R3 specifically, and in this class we're only going to cross vectors that are three-dimensional. So if we take two three-dimensional vectors, A crossed with B is going to be a vector itself. That's how we're going to multiply two vectors and we're going to get a vector back. And I'm going to tell you more things about what that means, but it's going to be a vector in its own right, and so maybe I'll just like set up, I'm going to write it as a column. Okay, how would we actually compute that? I'll actually just show you that. Suppose U equals 206 and V equals -5 to -1. Okay, find u cross v. Okay. U crossed with v, we're going to set up I, J, and K. Realizing I have not defined that, and since the first video in my series, I should probably do that. Okay, just off to the side, I'm going to define I is in 3 dimensions, that's 1, 0, 0. J is the unit vector in that y direction, 0, 1, 0. You probably can't even see this, blocking. And K is equal to the unit vector in the z direction. It's going to be 0, 0, 1. And like a lot of words I'm using, I've not really actually defined, but we will get through that over time. Okay, that's I, J, and K. So we've got I, J, K. U, we copy the numbers in U, 2, 0, 6. And V, -5 to -1. Okay. What we're going to do is we're going to say that this is equal to, we're going to set up for I, -j plus K. Okay. And when I say I, J, and K, I mean these. I'm not going to put the little accentuations on top of them because we're just trying to show you how to compute. Okay. So what we're going to do, we're going to take your finger or whatever and cover up the first column, the I one, when we're computing what's going to go right here. Okay. As we cover it up, we're going to multiply, and subtract. Okay. So 0 times -1 minus 6 times 2. Okay. Then we have minus j here, and the minus is for reasons that we're going to see later in the course once we learn about how to actually take determinants. Minus j times, okay, we cover up the j column. We do the same thing, we multiply, subtract. So 2 times -1 is -2, minus 6 times 5 is -30. Okay, there we are. Plus k, and we're going to do the same thing, we're going to cover up the k, and we're going to multiply, and subtract. So 4 minus 0. Which is like, if I was to add this all together, is -12i. Okay, so this is -2 plus 30 is 28, so minus 28j, because of the minus right here, plus 4k. And then, understanding what I, J, and K are, this is going to be equal to, if we're going to write how we write vectors in this class, that'll be -12, -28, and 4. Okay? We can do this, right? Okay, what else was I going to say here? Completely lost it. Okay, that's how we compute the cross product. Oh, yeah. So I need to actually copy down, it's going to be a formula in terms of A1, A2, A3, B1, B2, and B3. And so I'm going to pause the recording, write it down, so if a person wanted to copy it down, they could, but this is not the type of definition that you actually want to work with. You want to be able to take the cross product, using basically taking the determinant of this matrix, which you don't know about yet, but if you can just follow the process, like do the fish thing repeatedly, then that's all I need from you at this point, is to actually be able to cross 2 vectors and compute it reliably. Okay, so I'm going to erase all this, I'm going to put up the definition, and then it'll be there for you. All right, there you go. Okay, that's the definition of the cross product, and explicitly in terms of, I didn't close that parenthesis, but explicitly in terms of the coordinates of A and B, right? Okay, something I need to tell you about the cross products that I'm not even going to list as a theorem or anything, I'm just going to let you discover this on your own. We know that real numbers, we can multiply them and that commutes, right? 10 times 3 is the same as 3 times 10. Cross product does not commute, but it anti-commutes, which means that B crossed with A is going to be the negative of A crossed with B. And I think I'd like to let you just discover how that happens on your own. Okay, and thinking about the right-hand rule once we get there. That's another thing I'm not going to actually define or list as a theorem or anything, but the orientation of the cross product does respect the right-hand rule. So A crossed with B, if it was like that, it's going to go up, and if it's A crossed with B that way, it would go down. I mean, those of you who know about the right-hand rule, that's great. If not, I'll work with you on it if that is a necessary thing. I don't know if it's going to be. All right, these are kind of some facts. So the vector A crossed with B, right? That's orthogonal to both A and B. Okay. That's something that you can check, yourself when you cross two vectors. Go and just dot it with either of the two factors, and like we said over here, you'll get 0. Okay. So the vector A crossed with B is orthogonal to both A and B. That's the first thing. Not going to prove that for you. I don't think I'm going to be really having much proof in this video. Okay, I've got some theorems, not much proof. There's going to be a lot of proof in this course, just not today, I guess. All right, and let's see. Okay, area. This is the last thing. And this is something I didn't quite hit in class with people sitting in front of me. But if the area of a parallelogram Okay, so we can find the area of the parallelogram spanned by two vectors u and w. Maybe this is u and maybe that's w. Okay, and these are just, I'm not saying that these are two-dimensional vectors or three-dimensional vectors, they're just some vectors, right? There's a parallelogram. I think for the most part we're going to talk about this in space, but I don't know. I haven't thought about this. I'm not going to guarantee that this goes for higher dimension. Okay, so what we're going to do is we are going to find the area of this parallelogram by crossing u and w. Hi, hey, how's it going? Pardon me, I had a visitor, lost myself. So the area of the parallelogram spanned by u and w is equal to the length of the cross product. Okay, so it's the length of u crossed with the w or w crossed with u. Because it anti-commutes, at worst you're going to have the negative of the other one, they'll have the same length. Okay. So that's another fact. So if you say you were given a problem where you're given 3 points in space, and they make a triangle, and you want to find the area of the triangle, well, you could find turn the triangle into two vectors. Right? There's kind of like that. Find the area of the parallelogram, divide it by 2. Right? We can do that. Okay, that's something. I think there was something else I wanted to tell you. Oh, unit vector. I was supposed to tell you about that earlier. It's all right though. All right, so the last thing I want to tell you is how to find a unit vector in a particular direction, or any vector in a particular direction. Okay. Okay, so the unit vector in the direction of a vector A is, we're going to write it unit vector towards A, which is not necessarily to say that all of the vectors that we start off calling U are going to be unit vectors, which I understand it's a little confusing, but if we want the unit vector in the direction of A, we'll call it U sub A. What we do is we take, suppose this vector had length 10. You can't even see the tail end. But if it had length 10 and we wanted a unit vector that had length 1, what we could do is we could divide everything by 10, right? Make it 1/10 as big. So what we're going to do is we just divide all the components by the length. Okay, I've showed you how to find the length. If we take a vector and we divide it by, this is a number, that's still going to be a vector. It's going to be the unit vector in that direction. Okay, if we wanted a vector with length 8 in the opposite direction, we could just throw a -8 on that as well. Multiply it by -8. Okay, I think that's the thing I'm going to ask you to do in the homework. But that's all I got for you for now.